Alright guys, hoping to make a quick video to kind of take you through this whole process of calculating the forces on truss members. Here's our basic diagram. What we're starting with a real basic triangular truss. This triangular truss is actually an isosceles truss, so our two diagonal members here, AB and BC, are equilateral. They're the same distance, and so we can kind of drop this down, and we know this distance here is the same as this distance here. First thing we want to do, draw a quick diagram. And when we do that, we end up with something that looks like this. We've got the 100 Newton force coming down. Establish your pin, and once you've placed your pin, we've placed it at A. So we know that at the pin we've got two forces acting, a force at A in the X direction and a force at A in the Y direction. Over here, here's our roller. And at the roller, we've only got one particular force, and that force is acting in the Y direction. So the next thing we need to be able to do is to use those equations. Because we know this thing is in static equilibrium, we've got three equations. The sum of the forces in the X are going to be equal to 0. The sum of the forces in the Y are going to be equal to 0. And the sum of the moments about our pin at point A are also going to be equal to 0. So let's piece this together. Should be a pretty relatively easy, quick calculation. Sum of the forces in the X, we've only got one force acting in the X, one external force acting in the X direction. So quick and easy here. The force at A in the X direction, that's the only one, so we know that it's got to be 0. Looking at the forces in the Y, we've got three. The force at A in the Y, the 100 Newton force coming downward, and the force at C in the Y. These two are our reaction forces, so let's go ahead and piece together what we know. We know that the force at A in the Y direction plus the force at C in the Y direction, these are both positive, they're going upward. And then our 100 Newton force coming downward, we need to write as minus 100. And based on our equation, those have to add up to 0. Let's just simplify this. We've got two unknowns in this particular equation, so we're not going to be able to solve for anything explicitly. All we can do is simplify and hope that we can come up with something useful that we can plug back in later, which we will. Alright, the last piece of calculating the external forces is to calculate the moments about A. And again, just a reminder, what we're going to have to do here is take into account all of the forces, the force at A in the X, the force at A in the Y, the 100 Newton force coming downward on this truss, and then the force at C in the Y direction. And we need to take those into account relative to their position to the pin, so how far they are away from the pin. Force at A in the X is at the pin, so it's got a position of 0. That's in the positive direction. Force at A in the Y direction, again, it's at the pin, so it's got a position of 0. The force at C, let's go up here to the 100 Newton force. It's coming downward, so it's minus 100. In its position, it is 5 away. The force is being applied 5 units away from the pin. And then lastly, we've got the force at C, and that's a positive force. It is 10 away from the pin. And we've got 10 times the force at C in the Y direction. All those are going to sum up to 0. And we can go ahead and simplify some things in this equation. 0 times anything, that's going to eliminate these two here. This is negative 500. Plus 10 times the force at C in the Y direction. We're going to move this 500 over. So add 500 to both sides. And we're left with the 10 times the force at C in the Y direction is equal to 500, which gives us the ability to solve for the force at C in the Y direction, and that's equal to 50. So 50 newtons in this case upward is the force at C in the y direction. That was terrible. Let me redo that. So now that we've got one of these forces solved for, we can come back over here and plug in to this equation. We can figure out what the force at A in the y direction is. Plugging in very simply, we get plus 50, subtract 50 from both sides, and we find that the force at A in the y direction is also 50 newtons. And that makes sense because it is it's an isosceles triangle, essentially, our truss is, and so this 100 Newton force, the reaction forces at both joints here, are going to be equivalent at 50. The next step in this process is to figure out the angle measures, and we're going to do that with some basic trigonometry. We're going to focus in here on point A in this intersection here. So what we've got essentially is this triangle, if I can draw it nicely. Not much better, but hopefully you guys get the point. This thing has a height of 5, and it's also got a base length of 5, and we're trying to figure out what this angle is right here. So it's a right triangle. We can use our right triangle trig. So what we know is that the tangent function is what relates the opposite to the adjacent. So the tangent of theta in this case is going to be equal to 5 over 5. Go through, solve. Inverse tangent of 5 over 5 is going to give us a 45-degree angle. Same thing over here for this triangle. Here's my triangle. Here's the angle that I'm interested in. And it's essentially just the same calculation. Our height is 5. This distance down here on the base is 5. And so same process, tangent of theta equals 5 over 5 allows us to figure out that that angle measure is also going to be 45 degrees. Alright, so the last step in this is to create a free body diagram for each joint. We want to include all external and internal forces. I've included our angle measures that we did in step 2, and I've gone ahead and done that. So what we want to do is we want to look at all the forces at each joint using our known information and the equations of statistics. So here's the free body diagram at A. The free body diagram at B looks like this. And the free body diagram at C looks like this. So what we want to do is just take it one joint at a time. We'll start here over at A. You can see I've highlighted that joint A and kind of enlarged it. We know that this angle is 45 degrees from step 2. And we want to use our equations of statics. We know that the sum of the forces in the x direction are going to be equal to 0. So let's look over here, see what forces are acting in the x direction, and we can set up an equation based on the sum of the forces being equal to 0. Our first force is the force at A in the x direction. The next one we see that's acting in the x direction is the force of AC in the x direction. And we've got this diagonal force here, this diagonal member, AB, and we need to figure out how much of this member is being applied, or how much of the force on that member is being applied in the x direction. That would be the x component of this thing. So if we just kind of simplify this, this is AB. We know this is 45. So we can set up some expressions using our right triangle trig that we know are true. Here we're dealing with the x direction. So what we want to do is, this is the amount of force that's going to be applied in the x direction, is this base right here on this particular joint. So what I know is that the cosine is the function that relates the adjacent, in this case, to the angle, to the hypotenuse. So the cosine of 45 is going to be equal to this base right here. That's the adjacent. And in this case, we've got the hypotenuse labeled as AB. And we can solve that for the adjacent side and come up with an expression of AB times the cosine of 45 for that particular side. So we come back down here, plug that into our equation. So we've got plus AB times the cosine of 45. All of that's going to be equal to 0. We know from our previous work that this is 0, so that's going to drop off. And we can simplify this again. We're going to have two unknowns, so can't necessarily solve or find an explicit answer for either one of our unknowns, so we'll have to come back to this equation. Next thing we want to look at is the forces that are acting in the y direction. So again, we know an expression for that, or we know based on our equilibrium equation, the sum of the forces in the y are going to be equal to 0. Let's go back to our free body diagram. We know the force at A is acting in the y direction. And we previously solved for that force. We found out that it was 50 newtons. So this is 50 newtons. We've also got the y component of our diagonal member here, AB. Again, we're going to take the same process and come up here with and try to find an expression for this side. And when we do that, we can go through. We know that the sine function is what relates the opposite relative to the angle to the hypotenuse. So the expression for this, again, we're going to solve very similar to what we did down here. And the expression for this particular side is going to be AB times the sine of that angle. So FAY plus AB times the sine of 45. Those are the only two things that are acting in the y direction. So those have to add up to 0. Well, again, we said we know that this is 50. So we can subtract 50 from both sides. And we get an expression that looks like this. Negative 50 on the right side now. And we're going to go ahead and divide by the sine of 45 in order to solve for AB. And now we get an explicit expression for AB. Plug that into your calculator and you'll find that AB is equal to negative 70.71. Take that, go back over here. We can plug that in using substitution. And we can now simplify this thing and figure out what the force of AC in the x direction is by solving. So the force of AC in the x direction, we can move this over. So we end up with negative AB times the cosine of 45. Well, we know AB is negative 70.71, so that turns into a positive. And we plug this into our calculator, and we end up with the force at AC in the x direction is equal to approximately 50 newtons. Because we rounded this, we'll get something that's not quite 50 newtons, but when it rounds up to 50 newtons. And we've got that expression for the force of AC. Alright guys, the next piece of this then, we want to focus in on this joint over here, joint C, and take a very similar process. There's one main difference that we'll talk about here in a second. So looking at our equilibrium equations, we know the sum of the forces in the X is going to be equal to 0. Looking at the free body diagram at C, we see that FAC, which we've already solved for up here, is 50 newtons, but in this case it's pointing again away from the joint. This is how we always model our joints. We have our forces initially pointing away from them. So that's actually acting in the negative X direction. So that ends up being negative 50. The other thing that's acting in the X direction is the X component of this diagonal member, CB. So what we need to do is find an expression for that thing, for this piece right here, the X component of this particular diagonal member, CB. So we solved for these angles before. Here's the big difference in calculating this. So we know that this is 145. From our previous discussions about the way that angles are measured, we want to start this at the X axis and wrap it around until we hit our vector. And that will actually give us the degree of this vector. So here, the complement of 45 is going to give us 135, so we need to use this 135 in our calculations here. Finding an expression, we know that the adjacent here, as it relates to the hypotenuse, the trig function that relates those two is the cosine function. So cosine, and again we're going to use 135 here, is going to relate the adjacent to the hypotenuse. And in this case, the hypotenuse happens to be BC or CB. Same thing there. Go through and solve for the adjacent side so that we can get an expression, and we end up with BC cosine of 135 is equal to that adjacent side. There's my expression. Alright, so here's the X component of this diagonal member, BC. So we come down here to our expression, or our equation, our equilibrium equation. We're going to add BC times the cosine of 135 and allow that trig function to figure out if that's going in the positive or negative direction. Those are the only two X components, so those are going to sum up to 0. And going through and solving for BC, add 50 to both sides, divide by cosine of 135, and we end up with an expression that looks like this, 50 over cosine of 135. Plug that into your calculator and you'll get an expression, or you'll get the force of BC is negative 70.71, and that matches up with the force here of AB, negative 70.71. So it looks like we did something right. Sum of the forces in the Y's at C, and if you notice, we've got almost everything in this thing. We've got one more piece to go, and that's the Y component of CB. We've solved for the force of AB. We've solved for the force of BC. This quantity is known. And so we go over here and piece together our forces in the Y. We've got the force of CY, which we solved earlier. We know that that's 50 newtons. In the positive direction. We need an expression for this guy now, the Y component of this thing, and we know that the sine function is the one that relates that. So similarly, we go through and we solve, and the expression for this would be BC times the sine of 135. So we're going to add BC times the sine of 135. And those are the forces in the Y direction. They're going to add up to 0. Same thing here. We're going to go through and solve for BC. So we need to move this over. That ends up being negative 50 On the right side, we're going to divide by sine of 135 to isolate BC, and we get an expression that looks like this. That's equal to BC. So you finish this off and you end up with BC equals negative 70.71, but actually we've already solved for BC, so we didn't actually have to do this last part. This is a little bit of extra work. If you look at the free body diagram, we've got all of these forces. We've got BC here. We've got the force of AC that we solved for before. And so what we end up with, ultimately, we can list out exactly what we found, and I'll do that on the next page. Alright guys, so the last thing we need to do is figure out if these things are in tension or compression. And all we're going to do is look at the sign of these particular forces. A negative sign is going to tell us that that particular member is in compression. So these two diagonals in this particular case, AB and BC, are in compression. These three are in tension, are under tension. And the force of A in the x direction is 0, so there's actually no horizontal force at the pin. So that's neither under tension nor compression. And that's it.